I am going to solve basically every projectile motion problem. So let me go ahead and start off with the definition of projectile motion. So if I have an object moving in the air and there's only the downward gravitational force of mg, there's no air resistance, there's no rockets, there's no nothing else. So once the time it leaves the launcher, whatever that launcher is, till the time right before it hits the ground, that whole time there's only that one force acting on it. That's projectile motion. Projectile. Okay, so if I have projectile motion, the following is true. The acceleration in the x direction is 0 meters per second squared because there's no force in the x direction. The acceleration in the y direction is going to be negative g, where g is 9.8 meters per second squared because there's a force in the y direction of mg, and that's equal to may, so the m's cancel. The other important thing is if I launch it with some angle, I'll call this V1. I'm trying to use V1 because you like to use V2. So if that's the case, then here is my launch with some angle theta. V1 is a vector, but I can find the initial x velocity, V1x, would be the cosine, right? I have a right triangle here, so it's going to be V1 magnitude times the cosine of the angle. And then I can do the same thing for the y component. V1y is V1 sine theta. Now, the other very important idea about projectile motion is that the motion in the horizontal direction and the motion in the vertical direction are independent. This velocity does not depend on, the x velocity does not depend on the y position or the y velocity if there's no air resistance. If there is air resistance, that's not true. Okay, so that means that I can break this into a problem that looks like this. In the x direction, it's just a ball moving at a constant speed. This is the ball every few seconds. In the y direction, it's a ball moving like this. It's slowing down, stopping, and then coming back down like that. So I can break it into those two motions, and with those two motions, I can treat them independently except for the time. The time this takes is the same time that takes. So let's say this is my x motion. Let's say just generically I start with a ball at a height y1 and a position x1. It doesn't even really matter what that is. I can have my origin anywhere. And then down here is going to be x2, y2. Again, I don't care where they are. You might care, but I don't care right now. So in the x direction, I can say x2 equals x1 plus v1x delta t, where delta t is a change in time. That's really the only important equation in the x motion, but I don't always have the time. So I can look at the y motion, and I get the following. I'm going to write down all the y equations. v2y equals v1y minus g delta t. That tells me how the velocity at the end of some time interval, which I don't know, right? But maybe I want to know where it is at the highest point. Well, I can say, well, I know v2y, right, is 0 up there, so I could solve for t. So there's a whole bunch of problems like that, and we're going to get into those. I could say y2 equals y1 plus v1y delta t minus 1/2 g delta t squared. This is your basic kinematic equation. If I know where it starts and where it ends and the initial velocity, I can use this to solve for the time. And then I can plug that time in over here. And then finally, I have this one, v2y squared equals v1y squared minus 2g y2 minus y1. So this isn't used that much because mostly what we do is to find delta t here and then use it over there. Now, if I have a problem like this where I shoot it off a cliff and it lands down at the bottom, this equation is going to be bad because y2 is 0, but y1 is not. The y velocity initial is not 0. So I get a t, a constant, and a t squared term, so you have to use the quadratic equation. So solving these is mathematically challenging in some cases, but we're going to do it a different way. We're going to use Python to solve all of these problems. Okay, so the idea is this. Suppose I go back over to my ball, launch with some velocity v1 vector at some angle theta, it doesn't really matter. And I break, instead of finding out where it lands, I'm going to say, where is it? After some new delta t equals 0.01 seconds. I picked a value. You can pick whatever value you want. I picked 0.01 seconds. So during that time, I can say the following. I can say, I know the acceleration. I'm going to write this as a vector. The acceleration is g, right? Which is equal to 0, negative 9.80 meters per second squared. So that's my x, y, and z component of the acceleration, which is g. I also know that the acceleration can be defined as the change in velocity over the change in time. So if I have this short time interval, so this is going to be t1, and now I'm right here at t2, then that's going to have a new velocity, v2. So if I write this out, I can say v2 minus v1 over delta t. And I'm going to use this as vectors because it's going to make it easier in the long run. I'm not going to break it into x, y, and z's. I'm just dealing with it as vectors. I'm going to multiply both sides by delta t, and I get v2 minus v1 equals a delta t. Now I'm going to add v1 to both sides, and I get v2 equals v1 plus a delta t. That is so important that if I had a marker that was different, I do. I'm going to put a green box around that. So this says if I take my acceleration and multiply by my time interval 0.01 seconds, and I add that to my velocity that I started with, I'll get the velocity at the end of the 0.1 seconds. Yay. And that's pretty cool. Now I can do the same thing for position. So here's my origin. Actually, let me put the origin right here. So here's my initial location. I'm going to call that the vector r1. And then a little bit later, it's over here at vector r2, where again, r1 is going to be equal to x1, y1, z1. They're just numbers, right? It doesn't really matter. I have x and y and z components. I don't really care. And the same thing for r2. So, but I can write the average velocity. I can say v average is the change in r over the change in time. That's how it's defined. So this is going to be equal to r2 minus r1 over delta t. Now I can multiply both sides by delta t, and I get r2 minus r1 equals v average delta t. Now I can add r1 to both sides, and I get r2 equals r1 plus v average delta t. And you notice it looks a lot like this equation, and it does. Okay, so what this says is if I know the average velocity from here to there, which I technically could get, right, because I just calculated the final velocity. If I know the average velocity, I could use that to find the new position after 0.01 seconds. But I want to make it a little bit easier. What if I have a short time interval, then v2 is very close to v1. It'll be different, but close. So what if I say v average is approximately equal to v2? Then I can write this as r2 equals r1 plus v2 delta t. Guess what? I'm putting a box around that. So it turns out that if my time interval is small enough, this works very well. Okay, so and it's a little bit easier. It's not so much more. You could do it a more complicated way, but I like to do it the simplest way that works. So what this says is after a short time interval, I can calculate the velocity and I can calculate the new position. And then if I want to calculate where it is at time t3, I just do the same thing again. Now I calculate v3 equals v2 plus a delta t. And then over here I say r3 equals r2 plus v3 delta t. And then I can do the same thing for 4. I can do the same thing for 5. I can do the same thing for 6. I can break this up. Now, if this takes 1 second to get over here and have a time step of 0.01, that means 100 of these calculations, and nobody wants to do that. I don't want to do that. You don't want to do that. Maybe someone wants to do that. But I don't want to do that, so we're going to do this. We're going to do this calculation in Python. Okay, so let's switch over to Python. And now, one of the things that is important about this, it's called a numerical calculation, because now, in order to do this, we actually need numbers, right? If I just write this down as an equation, it doesn't help me at all. But if I know the numerical values here, then it will help. So let's pick some values. I'm going to launch this ball off. This is a table. So R1 is going to be equal to, let's say, 0, 1.20 meters. V1, it's going to be equal to, let's say, I'm thinking of these balls that we can launch. 4 meters per second times cosine of 20 sine of 20, 0. And yeah, so I have the starting, need the starting positions. Okay, so let's go over to Python. Switching to Python, here we go. Python. Can you see that okay? Is that too small? Let's make that a little bit bigger. People like big. Okay, so this is trinket.io. It is a place where we can do Python. And one of the nice things about this one, it uses GlowScript VPython, and it has built-in stuff for both graphing and vectors. And it's going to make your life much easier. Of course, you could do this on paper. You could do this in Java. You could do this in C++. You could do it in Fortran, COBOL, BASIC. But we're going to do it here. Okay, so let's just write down the things that we know to begin with. First, I'm going to say G equals vector 0, negative 9.8, 0. And so now let's just do this print G, and you can see that it does indeed give me the vector there. Okay, so that is working. Now I need my initial position. R equals vector 0, 1. What did I say it was? 1.2, 0. And these are numbers. Even though they're vectors, they're still numbers. So we don't put units in there. Okay. The units are the human's job. V equals 4 times vector, times vector. Let's just do this way. Let's say theta equals 20 degrees. Now, the default trig functions in Python are in radians. There is a way to do it in degrees, but I'm just going to convert this over to radians to multiply by pi and divide by 180. So now that's in radians. Now I take the vector 4 times cosine of theta. And I'm doing it this way so I can change this fairly easily if I want to, and I will want to. Now I need one other thing. Time equals 0. Let's put it like this. dt equals 0.01. Yeah. So now we're going to launch this, and we're going to do exactly what we said. So I'm going to do it in a way that doesn't really work that well. I'm going to say while t is less than 0.05. Do the following. No, 0.5. Do the following. 0.2. I'm making it smaller. So the time thing, it makes more sense to people. I understand. I'm going to do it until the time the value of t is not less than 0.2. Now, the first thing I want to do is to update the velocity, just like I said before. So I'm going to say this. V equals v plus a. Oh, I'm going to say plus g. Yeah, I should say a. Let's do this. A equals g. That makes me feel better. Okay, a times dt. So that did it. But notice that I don't have v1, I don't have v2, I don't have v3. I just have v. Because this, in Python, this says take the value of velocity, which is up here, this vector value, and then multiply the acceleration, which is this vector value up here, times dt, and add those two together, and then put that in the little space where I have the velocity stored. It's stored as a number there. So I don't have to worry about all these different indices. I'm just changing the actual velocity. I lose the old stuff, but that's fine. I don't really need it. I only need the current one. Now I'm going to update the position. R equals R plus V times dt. And you see the same thing. That's R1 and R2. But you see why I went with V2, right, instead of V average. If I wanted to do V average, I would need to do a trick. Because I've already changed the velocity. I don't have the previous velocity anymore. So I'm just using the newest velocity. It makes the program a little bit easier, and it turns out that it does indeed work. So we're cool with that. Now I need to do one other thing, and that's update the time, right? I need to change time. So t equals t plus dt. So now I've updated it by 0.01, and that's that. And then when I get done, let's just go ahead and print r equals, where is it going to be? R. And we'll put the units down, meters. Okay, so I should save this, but I'm not going to. Okay, so there it is. So it went higher. So it started at 1.2. A is, oh yeah, it went higher. That's fine, because I shot it up at an angle. Okay, so it went higher during that time. But the real question is, when would it hit the floor, right? So what I could do is I could say, oh well, it didn't hit the floor yet. Let's print it out. Let's run it for a fifth of a half a second. And now it's closer to the floor. It's now moving down. I could increase this even a little bit more, 7. And now it's below the floor. I'm going to call the floor at y equals 0. So I could keep adjusting this and to find out where it landed. And then I have my x value right there. There's my x coordinate right there. I can find out how far it went. Okay, but let's do this a little bit better way. One, I could say keep running the simulation until r gets to 0. So I'm going to say this. While r dot y is greater than 0, right? Because r dot y starts up at 1.2. When it gets down to below 0, stop. Okay, so let's run it that way. Be careful doing this because you can get yourself in an infinite loop. If I said, it can happen. Okay, so there you see it does go down to negative, but it's barely negative. And I get the range of 2.44. That's how far it went as I shot it off that table. Okay, that's useful. I'm done. I've solved every problem. Oh, I'm blocking the meter thing. I think it's good. I've solved every problem. Because I could change the initial velocity. I could make this, okay, now let's put this as V1. I'm going to call V1. And then I'll say V1 equals 3.3. Now I'll rerun it. It shouldn't go as far. It doesn't, 1.92 meters. What if I want to launch it at a greater angle? Let's say 35 degrees. Let's change that to 35 degrees. Done. See, so I can just change these initial values and I get where it went. Oh, what if I want to know the final time and the final velocity? I could do that too. Print t equals t seconds. That's how long it took to get there. I could say print v equals v meters per second. That's the velocity at the end. So I can run those, and there you go. I get everything I want. I have everything I want. Everything I could ever possibly want. It's right there. But I want more. I want more than I could ever possibly want. But this is solving every projectile motion problem. I could even say this. What if I want to launch it up onto a table? We're going to do that one. I'm going to do 2 problems, but let me first make a graph. So it'd be nice if I could plot the trajectory. I want to plot the trajectory of this ball. Where would it be in space? So literally x versus y. So to do that, I need to make a graph. So let's call graph G1 equals graph. Graph is a built-in object in Python, and it has properties like the x title, the y title, the title, the width. I'm not going to put a title. I'm just going to put x title. So let's say x title, and I'm going to do this easy, equals x in meters. Y, and you could call this whatever you want. You can't call y title whatever you want. But once I put the quotes, I can say whatever I want. And I'm also going to do this. If you run out of room, you press return and you can keep going as long as you put a comma on the end. And so let's say width equals 450, height equals 250. That way the graph will just make it a little bit better. But that doesn't plot anything. I need to actually make a function to plot, and I'm going to call this F1, and there's another object called G-curve. If you just make G-curve, it will make a graph, but in order to put the labels on the axis and all that stuff, you need to make a graph first. And this is going to be, let's give it a color blue, because I like that color. So then down here in my loop, I need to add a data point to that graph, and that's going to be f1.plot. And I need to add my x and my y coordinates. So I can say my x coordinate is r.x, my y coordinate is r.y. Let's run this sucker. Okay, I do need to move this now. Let's move that out of the way. You still want to see me probably. So there you go. There's my trajectory of the plot. See, I launch it off at an angle. It's still not quite small enough to see. And it lands down here at 0. If I want to find out how high I can get, I could actually just use the graph, right? I can move my mouse over that and say, oh, there's the highest point. And my y coordinate at the highest point is 1.39. Okay, that's pretty cool. So there you go. That's every graphing problem. Now let's just change let's change the angle. Let's change the angle to -10. So now I launch it at an angle below the horizontal. I can do that. No one can stop me. And there you go. How far does it go? Okay, let me switch over to paper. I just came up with a fun problem. I'm actually just going to solve one problem because I don't want to go on too long. And it's this. Let's switch. So I have a baseball, and there's no air resistance on this baseball, and I'm standing on a cliff. So like this. I'm up here. And let's say I can throw this baseball with a velocity of magnitude of V1 is 15 meters per second. I'm not that great. And down here is a little toy car that starts right at the base, and it moves with a constant velocity of V car equals, let's say, 4 meters. I'm making up stuff as I go. 4 meters per second. Okay, now I want to throw the ball such that this goes like that, and it lands in the car. That's actually not too difficult of a problem to solve, to tell you the truth. I just realized. But let's say that, should I pick the angle or should I pick the time? Let's say I know. Let's say they launch at the same time. They're going to launch at the same time. So they both start at t equals 0 at x is equal to 0. So t equals 0, x ball, which we'll just call x is 0. This is going to be equal to how tall should my cliff be? Let's say it's 4 meters tall. So y1 equals 4 meters. And then that starts at x car equals 0. And so I want to calculate what angle I need to throw this at in order that it will hit the ball. This you can solve analytically. It's really not too difficult. It might be a lot more difficult if this is accelerating, which would be cool too. And we'll change that. So the next, I'm going to do this with this, and then I'm going to say VC equals 4 meters per second. AC is going to be negative 0.2 meters per second squared. So it actually starts off and slows down. This is for fun. That's going to be part 2. So what I'm going to do is make a model for this, make a model for that, and just plot it. I'm going to plot the x positions as a function of time. I'm not going to plot the y positions. So let me first start with I already have this working. Let's just add in a car and change my graph to x as a function of time instead of y as a function of x. Okay, so that's the problem. I made it up right off the top of the bat. So going back over here to the computer, the first thing I'm going to do is change my graph to time and x. Now let's go ahead and run that. So down here, I'm not going to plot x and y. I'm going to plot t and x, t and r.x. And just make sure it's working. Right there. Okay, so that's exactly what we expect, right? The horizontal velocity of the car is, the ball is constant. And that's a constant velocity. Okay. I'm thinking this is just too easy of a problem, because what's going to happen, you can see in order to make this thing hit, the velocity of the car has to be equal to the velocity of the ball. I'm kind of disappointed. What if I just do the acceleration one? I could do the time. Let's just do the acceleration one. Okay, so let's make another graph up here. F2 equals G curve. Color equals color.red. And now I need some other variables. So I'm going to say X, let's say RC is the position of the car. So it's going to have a position 0, 0, 0. I need VC equals vector, I said 4, 0, 0. And AC is the acceleration. It's going to be vector negative 0.2, 0, 0. So that one's going to be slowing down. Yeah. Okay. So now let's just go ahead and launch this thing. I'm going to launch it at my angle of, let's start with a 20-degree angle. So down here, I need to also change the velocity and the position of the car. So I need to have two objects, VC equals VC plus AC times dt, and then RC equals RC plus VC times dt. And time is, there's only one time. And then down here I need to make two plots, f2.plot, t and rc.x. Okay, let's run that. So that doesn't look like it's even accelerating. Let's increase that acceleration to 0.8. Let's see if we can see it. I want to see this thing curve. Let's make it 1.8. It's curving now. Okay, let's make it 3.8. Okay, so there we go. So now you can see here that this runs until the blue thing, that's actually at y equals 0. I should actually make two graphs. But I could, but I won't. But I want to find out where they cross. And you see right here that the time they cross, but I want to change the angle so that they cross right here at the end. So I need to launch it a little bit higher. One way to do that is just to change this angle. I'm just going to change this to 25 degrees. Okay, that made it worse. Let's change it to a lower degree, 15 degrees. That's also worse. So maybe that it just looked worse, 35 degrees. Okay, yeah, there we are. So now we're very close. If they're matching right there, then it's going to hit. This is at y equal, this is when it hits the ground, y equals 0. So let's increase this a little bit more. One of the things you have to be careful of is that it's possible that it might not ever hit, right? It's possible that, well, I can always aim down. So increase a little bit more. And I'm doing this the old-fashioned way of just roughly changing things and until it no longer hits and then go back. That's pretty close. 39. There you go. That's it. So the ball is launched. Its horizontal velocity is constant. The car starts off with a higher velocity and slows down, but they still meet at the exact same time. And that's a fun projectile motion problem. But any projectile motion problem you can see using this numerical value, we can get these plots of the positions of different objects and do fun things. So I'll stop there, have fun. I'll include the code down below and just play with it. Playing with it is what's going to really help you understand how these things work.